So if you want to learn vector databases in one shot, then this video is for you. In this video, I will literally hold your hand and teach you everything from scratch. No prior knowledge is required. I have 15 years working as a software engineer and 4 years working as a lead AI engineer. And let me tell you, vector database is something you must know in 2026. Whether you are a software engineer, an AI engineer, or a machine learning engineer. Today, technologies like AI agents, recommendation engines, RAG application, enterprise knowledge bases are all powered by one core concept, vector databases. So by the end of this video, you will not only understand vector databases conceptually, but you will also gain hands-on experience working with vector databases. So here is what we will cover. So in chapter 1, we will understand the fundamentals. What exactly is a vector database, why were vector databases introduced, and how they work internally, and why they have become one of the most important technologies in the AI era. We'll also explore some real-world use cases used by companies today. In chapter 2, we will take a step back and understand what a vector actually is, because before understanding vector databases, you need to understand vectors and vector similarity. In chapter 3, we will dive into tokens and tokenization. You will learn what tokens actually are and why AI models don't understand raw text and why tokens are not the same as words and how tokenization becomes the first step in the embedding pipeline. In chapter 4, you will learn how text is transformed into vectors and how it captures meaning and context, and how vector math works behind the scenes, and we'll also explore the embedding models used in production AI systems today. In chapter 5, we will work with the Google Gemini embedding model, where we will see a complete live demo of generating vector embeddings. And then in chapter 6, we will go deep inside a vector database. We'll uncover the internal architecture, storage mechanisms, indexing strategies, similarity search algorithms, and how these systems scale to billions of vectors while maintaining blazing fast performance. And finally, in chapter 7, we will put everything together in a complete hands-on project. We will generate embeddings, store them inside ChromaDB, and perform semantic search using vector similarity so you can see the entire workflow in action. So if you are someone who wants to master vector databases, this video is for you. So grab a cup of coffee, open a notebook, and let's master vector databases together from zero to advanced. So let's get started. Today is the day 1 of the vector databases 0 to Hero series. In this video, we will be exploring what is a vector database, how does a vector database even work, and why do we even need vector databases? What is the need for vector databases? And also we'll explore some vector DB use cases. So let's get started. Okay, now let's start with the definition of a vector database. A vector database is a database designed to store, index, and search high-dimensional vector embeddings generated by embedding models enabling semantic search. Now at first glance, this definition might actually feel a bit confusing, and that's completely normal as it hides several fundamental concepts that power vector databases. And I'm sure your curious mind already has few questions like, what are these high-dimensional vector embeddings, right? And how are these vector embeddings generated by the embedding models? And what do we really mean by semantic search, right? So these are few questions that might come up at this stage. And once we get past all these concepts, right, even deeper questions start to come up. Like, for example, how do vector databases index these high-dimensional vector embeddings? Or how are we able to search through these high-dimensional vector embeddings so efficiently, right? So these are the key concepts that we will break down and understand step by step as we move through the course. So at this stage, if this definition is a bit confusing, that's completely normal. be rest assured that towards the end of this course, all these concepts would be crystal clear. Now, in this lecture, let's go one level deeper and understand how a vector database actually works step by step. By the end of this lecture, you will clearly understand the entire vector database pipeline. At a high level, almost every vector database follows the same core pipeline, regardless of the vendor. So let's break it down. First, we take our raw data. This could be text, images, documents, code, or anything else, and then pass it into an embedding model. Now, what is an embedding model? An embedding model is a machine learning model that converts data into numbers in a way that preserves its meaning. So here the embedding model's job is simple. It converts raw data into a long list of floating point numbers. Now, what are these floating point numbers? These numbers capture the meaning of the original data. Now, these are also called as vector embeddings. Now, don't worry about vector embeddings for now, as we have a dedicated lecture on that later. But for now, just know that it means that two pieces of content that has similar meaning will have vector embeddings that are close to each other in the vector space. Okay, now these vector embeddings are stored inside the vector database, but these vector embeddings are not stored alone. Along with these vector embeddings, you can store some reference to the original content, and also you can store some optional metadata. Now, I want you to pause here for a moment and imagine that you have stored 1 million images in this vector database. Now, to find the most similar images to a query image, you will have to search through all the 1 million images, and that would be a very slow operation with a complexity of big O of n, because it's just a linear search. So to make search faster, at this point, the vector databases under the hood performs vector indexing. And this is where the actual magic happens. So instead of scanning millions of vectors one by one, the database builds indexes using different approximate nearest neighbor search algorithms to make similarity search extremely fast. Now, don't worry about vector indexing for now, as we have a dedicated lecture on vector indexing where we'll cover all the different approximate nearest search algorithms. Now, different databases use different techniques here, but the goal here is always the same: fast and accurate search. So everything we have discussed so far happens in what we call the ingestion phase. Now, let's look at what happens when a user actually searches. When a user or an application sends a query, for example, let's say user searches, how do I improve my focus? We pass that query through the same embedding model. Now, I want you to pause here for a moment and think, why the same embedding model? It is because all the embeddings must live in the same vector space to be comparable. That is why we need to use here the same embedding model. Okay, so once the query embeddings are generated, the query embedding is then used to search the vector database. So here, the vector database internally searches the vectors that are most similar to this query vector or query embedding. And once the nearest neighbors are found, in the post-processing stage, the results are ranked by similarity score, and then metadata filters are applied if needed. And finally, the top k most relevant results are returned. And these concepts, whatever we just learned so far, is what powers your semantic search, recommendation systems, RAG pipelines, and modern GPTs. Okay, so to summarize here, overall, we can split the entire pipeline into two phases: the ingestion phase and the retrieval phase. Now, obviously, different vector databases optimize this pipeline in different ways, but the core idea remains exactly the same. So why do we need vector databases? Now, before understanding the need for vector databases, let's try to look at the types of data that we have today, right? So first we have structured data, right? Which are like tables, rows, fixed schema, right? So this is all structured, right? And then we have semi-structured data, right? Like JSON, logs, events. And then we have unstructured data. For example, your texts or PDFs, audio, video, images, right? These unstructured data, right? This data is actually high dimensional, right? It is unstructured, and this data is all meaning based, right? So the thing is that traditional databases cannot store this data, right? You can store it, but you cannot store this data at scale and perform search on this data, right? So that is where the traditional databases would struggle. So vector databases mainly target this unstructured data. We can store these unstructured data inside vector databases. Okay, now you might ask here, okay, what's the problem with traditional databases? Why we are not able to, search this unstructured data inside traditional databases? Because the problem is that traditional databases, they perform keyword-based search, right? Because these traditional databases are optimized for exact matches, right? You can do some exact keyword match within traditional databases, or you can do some range queries or joins and transactions, right? But the limitation for traditional databases is that whatever data you store here, it doesn't understand the meaning, right? So that is where if your keyword search would fail, then the traditional databases would struggle to retrieve this information that is stored inside traditional databases, right? So for example, if you try to store a PDF, the only thing that you can do here is perform some keyword-based search, but if that keyword is not present inside the PDF, right, even though the user intent is same, it will not be able to retrieve that information, because here the only thing that you can do is you can do keyword-based search. You cannot do semantic search. You cannot do meaning-based search, right? That's the main limitation of traditional databases. And whereas inside a vector database, you can perform semantic search. So you can search these information, whatever information you have stored here, you can search based on meaning, right? That's the power of vector databases. Okay, now let's try to take this one step deeper and understand what makes vector databases so different from traditional databases, right? So vector databases are designed to store high dimensional vectors, even thousands of dimensions you can store inside vector databases, right? So you can store high dimensional vectors. We'll understand what are vectors later in this course. For now, just understand that we can store high dimensional vectors inside vector databases, right? And these vector databases, they use vector indexes. They use the concept of clustering, and they use the concept of vector-based search, right, to optimize this search and make it more efficient, right? So using these algorithms, it also makes the search efficient, right? So the benefit we get is fast search. It can search millions of vectors in milliseconds, right? While also preserving the semantic meaning, right? So that is where the vector database is very efficient. So even if you have millions of documents, right, it can perform search efficiently because of these vector indexes. Now we will cover in depth, right, later on all these vector indexing techniques that are there inside vector databases. But for now, understand like why this search is so efficient because of these vector indexes, right? So here's the key point. So vector databases scale because they avoid the brute force search, right? They don't search in a linear fashion, right? They avoid this brute force search, and instead they use smart indexing and approximate nearest neighbor search techniques to find similar items in milliseconds. Now this is a very important concept, the approximate nearest search techniques, and we will cover all these techniques separately. But for now, this is what is actually powering your vector databases. And this is a very important thing to note at this point, right? This is what is the concept that powers vector databases. Okay, so now let's summarize the differences between the traditional relational databases that we have and the vector databases, right? So traditional databases, they work based on rows and columns, right? You can store your data in terms of some fixed schema in some rows and columns. You can perform keyword-based search, and the search is mostly done using where clauses, and it's schema driven, right? It's not that flexible, right? It's schema driven. So this is what we already know, the traditional databases. Whereas the vector databases, they can store vectors and embeddings. What are vectors and embeddings? We'll cover in the later lectures, right? What are vectors and what are embeddings, right? And so vector databases can store these vectors and embeddings. It can perform similarity search, again a new jargon which we will cover later. What is a similarity search? And it uses nearest neighbor search algorithms, again something we will cover later on. What are these nearest neighbor search algorithms and how they are used to perform similarity search? And the most important thing is that vector databases, right, because it can store all these vectors and embeddings, we're able to perform here meaning-based search, right? So it's all semantic search within a vector database, right? So these are the key differences between a traditional database and a vector database. Okay, now one important thing to note here is that the vector DB, right, your vector database does not replace the traditional databases, right? So in real world applications, right, this is the typical setup that you would find. The traditional databases are still used as the system of record, whereas the vector database are used to build a semantic retrieval layer on top of your traditional databases, right? So both are used together in any real world applications today. Okay, now let's explore some vector DB use cases. So vector databases are heavily used in building recommendation systems. It is used in building NLP-based search, where you can search using your natural language. The same technique is also used in building RAG pipelines to give more context to the LLMs. So vector databases power these RAG pipelines. Next, it is also used in building fraud detections and anomaly detection features. Now, these are just few use cases that I wanted to highlight here, but then there are many more similar use cases that you can build using vector databases. Now, in this lecture, we'll go through how it is used to build recommendation systems. So vector databases are used to power these recommendation systems, which you might have seen in some popular platforms like Netflix, Amazon, or YouTube. So all those recommendation systems that you see on these platforms are actually powered by vector databases. So how it works is that both the users and the items, they gets converted into vectors. So the user vector is nothing but the behavior of the users, like for example, what the users are clicking on, what they're watching, what is their watch history, or what is their purchase history. Those user behaviors are actually stored inside the user vector. And then you have these item vectors, like for example, the movie reviews, the product reviews, or like the actual product specifications. All those things, all those features are actually nothing but your item vectors. So both the users and the items, they are converted into vectors and they are stored inside a vector database. And then you can perform now on top of this data that you have inside the vector database, you can perform similarity search using the nearest neighbor search algorithms and then return the relevant recommendations to the users. So this is how you can build recommendation systems using these vector databases. Okay, so to wrap up this video, we covered a lot of ground in this video already. Like we understood what is a vector database, how does a vector database actually work, and we also understood the need for vector databases, and then finally we explored some vector DB use cases. So hope you found this video useful. In the next lecture, we will understand what are vectors, and we'll also understand this important concept of vector similarity. Thanks for watching. Hey everyone, welcome back. Today is the day 2 of the Vector Databases 0 to Hero series. In this video, we will be exploring what are vectors, and we'll also understand what exactly are vector similarity metrics. So let's get started. So earlier in this course, we understood that embedding models generate vector embeddings. Now, before explaining vector embeddings, let's first understand what are vectors. So when you hear the term vector, what comes to your mind? You might think of your math or physics class, and that's fine. But in the world of machine learning and vector databases, a vector has a very specific and powerful use case. So in machine learning, a vector is a one-dimensional array of numbers. It's just a one-dimensional array of numbers where each number represents a feature of an object. Okay, that's the definition of a vector in machine learning and vector databases. Okay, now let's look at few examples to solidify this concept. Okay, so for example, these are all valid examples of vectors. So this is a one-dimensional vector. Similarly, this is a two-dimensional vector, and this is an n-dimensional vector. Now, why all these are valid vectors? Because if you look at it, these are all one-dimensional array of numbers. So this is a one-dimensional array. Even this is a one-dimensional array. So that's the main thing you need to keep in mind, that it must be a one-dimensional array where each dimension, like for example, this is a two-dimension. So this 1.1 and 2.3 are actually representing the features of an object. Now let's look at some invalid examples. For example, this is not a vector. Vectors are represented in a one-dimensional array, and this is just a number, which is nothing but a scalar. Then you have this two-dimensional array. This is a two-dimensional array, which is also known as matrix. It's not a one-dimensional array. So this is not a valid example of vector. This is a matrix. Then you have this is a three-dimensional array. This is not a one-dimensional array. This is a three-dimensional array. Again, this is not a valid example of vector. So these are all invalid examples of vector. So that is what I wanted to highlight here, so that the difference between vector and examples which are not vector is very much clear. I think from this difference, you know that a vector is just a one-dimensional array of numbers. Okay, so keep that in mind. Now, before we move on, here's the question for you. are these vectors, whatever you see here, these valid examples of vectors, are these embeddings? Well, not necessarily. Like, all vectors are not vector embeddings. We'll cover what are vector embeddings later on in another lecture. So don't have this assumption that all vectors are vector embeddings. These are all valid examples of vectors, but all vectors are not vector embeddings. Okay, so that's something to keep in mind. Now there's one more part to this definition, that each number represents a feature of an object, and that is why these are also called as a feature vector. So now that we know what vectors are, let's understand what do we mean by dimension. For example, this is a one-dimensional vector. This is a two-dimensional vector. What does it really mean? So the number of dimensions is nothing but is equal to the number of features basically in that vector. So here you can see that there is a two-dimensional vector, so which means it has two features in this vector that we have considered. Okay, so to make this idea of features a little bit more intuitive, let's start with some concrete real-life examples. Let's try to describe a car using only one feature. Okay, so we can represent car A and we can represent its feature using a vector. So it's a one-dimensional vector where the feature we are considering is speed. So this car A can be represented in a number line and we can plot it somewhere, let's say here. So car A, and we represent it using the one-dimensional feature vector where the speed is 180. Now let's consider few more cars. So we have, let's say, car B and we have car C. So car B, the speed is 160. We again represent it using a one-dimensional feature vector, and car C, the speed is 80, again represented using a one-dimensional feature vector. And if you see here, we plot it on a number line. Now here is the important thing to notice, that cars which are like similar speed will be closer together, whereas the car which is having a different speed will be further apart. This is a very simple example where we consider just one feature, and that can be represented using a one-dimensional feature vector. Now let's try to add one more feature. Along with speed, now we consider, let's say, mileage. So this is now a two-dimensional feature vector. So a two-dimensional feature vector can be plotted in a two-dimensional plane. So you can notice here that cars with similar speed and mileage will cluster closer together, whereas the cars with different speed will be further apart. Now let's take this example further and let's try to add one more feature. Now add this price feature. So now we consider three features of a car: speed, mileage, and price. And it can be represented using a three-dimensional feature vector. So now you can plot a three-dimensional feature vector in a 3D plane. So again, it's a similar concept. All the cars that have similar speed, mileage, and price would cluster together in this 3D plane, and cars with different speed, mileage, and price would be further apart. So this is how you can plot it in a 3D plane. Now the thing is that in real-world machine learning systems, we don't stop at 4 features. We will learn later on that the embedding models, they can support up to 3000 dimensions nowadays. So those are extremely high dimensional vectors. A car can be represented with many more attributes. So we can consider the car safety, the weight of the car, the brand of the car, and we can just use n-dimensional feature vector to represent all its feature. And then the same concept, we can apply it to even n-dimensional. We can plot it in an n-dimensional vector space. Obviously, beyond 3-dimensional vector, the visualization becomes difficult, but the concept remains the same. So even in n-dimensional, so this is a 3-dimensional plane, but consider it to be an n-dimensional plane. Even in n-dimensional plane, the similar vectors would cluster together and different vectors would be further apart. It's the same concept that you can apply it to n-dimensional vector space. Now, why this concept is important and interesting is that when we learn about vector embeddings later on, you will see that the embedding models, they generate, embeddings which are like 3000 dimensional vectors, and obviously that is something you can plot it in a 3000 dimensional vector space. And whatever intuition I just try to build here with from 1-dimensional to 3-dimensional to 4-dimensional, the same concept you can apply it to even n-dimensional vectors. Then just few moments from now we'll learn about similarity metrics. So whatever concept you take away from those similarity metrics, you can apply it to 1-dimensional vectors, and the same concept can also be applied to n-dimensional vector space. So that is why this concept, building this intuition in the lower dimensional space, helps you solve problems when you try to think in the n-dimensional vector space. So I hope I'm able to stress here that how this concept is so important and how this concept will help you shape your understanding about vectors even in n-dimensional vector space. Okay, so the key takeaway from this lesson is that vectors are just nothing but one-dimensional array of numbers, and the number of dimensions in a vector space is nothing but the number of features that we have considered for that vector. More features will result in higher dimensions. So whenever for any object you consider more number of features, you will have higher dimensional vectors. Now similar vectors would be closer in the vector space, and different vectors will be further apart. Okay, so now that we know what vectors are, the next big question is, how do we figure out which vectors are similar and which are not? That's exactly what we will learn in this lesson. Okay, so what are similarity metrics? A similarity matrix is simply a function that takes two vectors as an input and returns a numerical score representing how similar these vectors are. Now this number helps us understand whether two pieces of data are close with each other or they're far apart in the vector space. Now different metrics define similarity differently, and that's what makes this topic interesting. So just remember that whatever we are going to learn about similarity metric is just a function that takes two vectors as an input and return the numerical score representing how similar they are. Now, in this lecture, we will focus on two of the most important similarity metrics. They are cosine similarity and Euclidean distance. So let's start with cosine similarity. So cosine similarity compares vectors based on direction and not size. So basically, cosine similarity doesn't care about how big these two vectors are. It doesn't care about the magnitude of these vectors. All it cares about is the direction of these vectors. So instead of asking what is the distance between A and B, all we care about is whether A and B are pointing in the same direction or not. So if two vectors A and B are pointing in the same direction, the angle between A and B would be very small, which means A and B would be in the same direction. And if this angle increases, it means they are in the different direction. Now we'll discuss in detail all these angles. For now, just know that cosine similarity compares vectors based on direction. So here is the formula to calculate the cosine similarity. So the numerator is the dot product of two vectors, and the denominator is basically the magnitude of those two vectors. Now the result of the cosine similarity is always between -1 to 1. This range directly comes from how the cosine function behaves. So that's why we always get this cosine similarity range between -1 and 1. Now when the cosine similarity is 1, that means the angle between two vectors is actually 0. And in simple terms, it means that both these vectors A and B are pointing in the same direction. whenever you get cosine similarity is equal to 1, it means that two vectors are similar. Now, if this angle is 90 degree, cosine of 90 is actually 0. So we basically get cosine similarity 0, which means these two vectors are orthogonal vectors, which means these two vectors are not related. They don't have any direct relationship between A and B. So whenever you get cosine similarity of 0, it means that those are orthogonal vectors. Then when the cosine similarity value is -1, and we get -1 when the angle is 180 degree, and what it means is that whenever the cosine similarity is -1, it means that two vectors A and B are in the opposite directions. Whenever you see this value -1, you can conclude that these two vectors are opposite vectors. So the difference between these orthogonal vectors and opposite vectors is, in orthogonal vectors we can conclude that these two vectors A and B don't have any relationship, whereas when these two vectors are in opposite direction, we can see that these two vectors are having some relationship, but it's actually in opposite direction, which means these two vectors are exactly opposite. So that's an interesting concept. If they're opposite vectors, they're related, but they're in opposite direction. Whereas orthogonal vectors means they don't have any relationship at all. So those are the few characteristics of the cosine similarity matrix. Let's try to solidify this concept with an example. So let's take two vectors, vector A and B, and these are basically the features of these two vectors. So vector A represents 2, 0, and 1, and vector B represents 4, 0, and 2. Now, first step, calculate the dot product. So the dot product is basically calculated by multiplying the corresponding elements of the two vectors and then adding them together. So basically here the dot product would be 2 into 4, then 0 into 0, and then 1 into 2. So when you multiply them and then add those multiplications, you get the dot product as 10. So that's the step 1, calculate the dot product. And then step 2, try to calculate the magnitude. So the magnitude is basically simply the length of two vectors. So once we calculate the magnitude of A and B, this is what we get. So then try to apply this step 1 and step 2 in this formula. So on the numerator, put the dot product, which is nothing but 10. And in the denominator, put the multiplication of the magnitude, which is 2.23 into 4.47. And if you just try to divide now, you get the cosine similarity approximately around 1. So here is the important insight, that even though these two vectors, vector A and B, the magnitudes are not same. We can clearly see from this that vector B is larger than vector A. So even though the magnitude is almost double, so vector B is almost double compared to vector A, this magnitude has no significance at all. So you can see that the cosine similarity is 1, which means both are in the same direction. That means that these two vectors have high similarity. So that is the important thing to note here, that in cosine similarity, all that matters is whether two vectors are pointing in the same direction or not. The magnitude is actually irrelevant when it comes to cosine similarity. And this is exactly why it works so well for vector embeddings, because in vector embeddings, the meaning is captured by the direction. It is not captured by the magnitudes. And that is why cosine similarity matrix is heavily used in vector embeddings, which we will see in the upcoming lecture. So here are the few use cases of cosine similarity. It is heavily used in search engines to match queries with documents. It is used in recommendation systems to find similar content. And then it is heavily used in RAG pipelines nowadays to retrieve the relevant context that you can feed to any LLM. So these are few of the use cases which depends on this cosine similarity, because for all these use cases, what matters is the direction of these two vectors and not the magnitude of these two vectors. So that's the only thing you need to remember about cosine similarity, that here the direction matters, not the magnitude. Now let's look at the Euclidean distance. So the Euclidean distance measures the straight line distance between two vectors in space. So unlike cosine similarity, this metric doesn't care about direction. Instead, it cares about how far apart these two vectors are in the vector space and what's the actual distance between A and B. That's what it cares about. So imagine you have 2 points A and B. If you draw a straight line between them, this length is nothing but the Euclidean distance. So if these 2 points are close, the distance would be small, and if these two are farther apart, that means the distance would be large. Now here's the formula to calculate the Euclidean distance. So we take the sum of all the squared differences and then take the square root. That's how you can calculate the Euclidean distance, and that basically gives us this straight line distance between A and B. So here are a few important properties of the Euclidean distance. You have a range. Obviously the distance range could be between 0 to infinity. So if both are like vector A and vector B are at the same point, then the distance would be 0, but the range can go up to infinity. If it is 0, it means both are identical vectors, which means both are the same point, exactly same point. Then only it is possible to get the result as 0. If this Euclidean distance is large, that means it is dissimilar vector. So those are the few important properties of Euclidean distance. Now let's try to understand this with an example. So now let's take two different vectors, A and B. So A equals 3, 1, 2, and B equals 6, 4, and 5. So first thing, we calculate the differences. So we just do 3 minus 6, we get minus 3, 1 minus 4, we get minus 3, and then we get 2 minus 5, we get minus 3. Then just square all these differences. So we get 9 plus 9 plus 9, which is 27. And then to find the Euclidean distance, all we need to do is find the square root of 27, which is 5.2. So this 5.2 is the Euclidean distance between vector A and B, and that is actually the actual distance between those 2 points. So that's how you calculate the Euclidean distance. So what are the Euclidean distance use cases? So it is used in GPS systems heavily. It is used in robotics. It is used in calculating the physical distance between two vectors, and it is also used in several spatial use cases. So you can see that Euclidean distance is heavily used in physical world, where the distance matters. Like what is the actual distance between A and B matters. The direction is irrelevant in these use cases. So that is when the Euclidean distance matters a lot. But in vector embeddings, and since we are learning about vector databases, I would say that cosine similarity is the most heavily used similarity metrics in vector databases. So let's quickly recap the key takeaways from this lesson. So similarity metrics compare two vectors numerically. Now cosine similarity focuses on direction. It tells us whether two vectors are pointing in the same direction or not. So in cosine similarity, all that matters is direction, whereas Euclidean distance, on the other hand, measures how far apart those two vectors are. So here the magnitude of those two vectors play a big role, and all that matters here is the actual distance between those two vectors. Now the choice between the cosine similarity and Euclidean distance, it obviously depends on the use case and the problem context. So obviously if you have understanding about what are cosine similarity and what are Euclidean distance metrics, then you would basically be able to apply to that problem context. So that is why understanding this is so important. Now, whatever concept we just learned, these are heavily used in semantic search. It is used in recommendation engines and building AI systems. Okay, so that's all in this video. In day 3, we will be understanding what are tokens. Thanks for watching. In this video, let's understand what are tokens. So what we will cover in this video is that what is tokenization, why do we even need tokens, and how tokenization fits into the entire vector database pipeline. So these are the key concepts that we will cover in this video. So let's get started. So earlier in this vector database pipeline, we understood that the embedding model is responsible for generating, vector embeddings. So what we do is we ingest this raw data and the embedding model generates the vector embeddings. But the thing is, these embedding models, they don't understand this raw data at all because this is in text format, right? Or let's say it's audio format or video format, but these embedding models, they don't understand this raw data. So what happens internally within this embedding models is that this raw data is first converted into something called tokens, right? And these tokens are nothing but just some numerical representation of this raw data. And then internally, these tokens are converted into vector embeddings, right? And that's something that is done within this embedding model. So you don't have to do that, right? It's done internally, but you should understand what are tokens, because the tokens are actually the modern currency, right? It's the currency based on which you are actually charged, right? All the embedding models, they charge you based on the number of tokens, right? Not based on the size of the data you're ingesting, but based on these tokens. And that is why having a solid understanding of these tokens is important, right? So with that motivation, let's try to understand what are tokens. So tokenization is the process, right, of breaking down the raw data, right, into something called tokens, right? That's what is actually tokenization. It is the process of breaking down the raw data into tokens, right? So what happens is that, let's say you have this, your raw data, it could be text, audio, video, anything, right? You have this raw data, okay? This is sent as the input, right, to this tokenizer, and what you actually get, right, what you get out of it is tokens, right? And how the tokens actually look, these are just array of numbers actually, right? So what you get is just some tokens, right? Okay, so this is what is tokenization, right? So you have this raw data, that's the input to the tokenizer, and the output is some tokens, some numerical representation of the raw data, right? That's what is tokenization. Okay, so the first type is character tokenization, right? Then you could also tokenize based on the words, right? So that's known as the word tokenization, right? And then there is a third type that's known as the sub-word tokenization, right? So these are the three types of tokenization that you will come across, right? So what is character tokenization? Let's try to understand these three types based on some example, right? So let's say that I have a text, I love vector database, right? Let's say we have this as the string, right? So in the case of character tokenization, what happens is every character, right? Every character is actually converted into some tokens, right? So how many characters you have here is some 13 unique characters. If you just try to check that, right? There will be 13 unique characters, right? So this will, using the character tokenizer, you would actually get 13 tokens, right? So using this character tokenizer, right, you would get around 13 tokens, right? So the problem with character based tokenization is that the number of tokens would be huge, right? And that's not an optimal solution, because if you have, just imagine for this small sentence, right, you would have 13 tokens, right? Because if you then consider, like a huge sentence, right, and all the combination, all the different types of characters, the number of tokens would be huge. So the thing is that the character tokenizer, the main drawback is that the number of tokens increases, right? That's the main problem, right, of the character tokenizer, right? Now, if you consider the word-based tokenizer, how many tokens would you have for, if you consider, let's say, the word-based tokenizer now, right? How many tokens you would get out of it, right? There would be like 5 tokens, right? Why 5 tokens? There are like 4 words, 4 distinct words, and then you have spaces as well, right? So you would get here 5 tokens, right? But then even the word tokenizer is not optimal, because if you see the English vocabulary, right, you would actually get, if there are like so many words in the English vocabulary, now you would have those many tokens, that's fine. But then there are certain words, like if you even consider the word tokenization, right, you would see that this word is made up of 2 subwords, actually, token and ization, right? And in English, there are many words that actually end with this, right? So token is already a word, we know that. And then there are many words that ends with ization, right? So if you consider now subword tokenizer, right? Yeah. If you consider subword tokenizer, it breaks down optimally words into smaller words so as to reduce the number of tokens, right? So we could have used word tokenizer, but then the problem with word tokenizer was that every word would be treated as a unique word. So even token could be a unique word, and tokenization could be a unique word, right? Whereas in English, we know that the words can be broken down into smaller subwords, and that is where all the modern tokenizer that you have for ChatGPT or any large language models, we use the concept of subword tokenization, and I will explain this now with few examples to clarify this, right? So I hope you understand what are these 3 types of tokenization. First, we have character tokenization, which is based on characters. Then we have word tokenization, based on the number of words, right? And then you have the subword tokenization that breaks down words optimally, right? Now, this is something that's not done just randomly, right? It is actually done with a lot of training to find the optimal what is the optimal way to reduce the number of tokens, right? And as I saw those examples, this concept would be crystal clear. Okay, so now let's head on to this OpenAI platform tokenizer, and let's start with this example that they have here, right? So if you see this example, right, so you can see that this sentence, this paragraph, right, that you have here, that is converted into 53 tokens. And it says here, like, many words map into 1 token, but then some don't, right? Like, for example, if you see here, indivisible, right, that is actually broken down into 2 tokens, right? But then if you see these initial words, many, then words map to 1 token, these are all mapping to 1 token, right? Now, then it says that the Unicode characters, like emojis, may be split into many tokens, right, containing the underlying byte. For example, this emoji, right, that you have here, that gets converted into 4 tokens. And then it says that the sequence of characters commonly found next to each other may be grouped together. Like, for example, 1, 2, 3 becomes 1 token, 4, 5, 6 becomes 1 token, and 7, 8, 9 becomes another token, right? So And if you want to see those token IDs, you can see, those token IDs as well. So the concept is very important here, that many words, they are mapped into one token, but some words they're mapped into multiple tokens. Then the Unicode characters, they gets mapped based on the bytes. And then we saw that sometime many common sequence of characters can be grouped together into one token, right? And this is all done based on the optimization that can be done to minimize the number of tokens. So you can see that if it was a character-based tokenizer, right, 252 characters, right, that would be 252 tokens, right? Whereas you have here just 53 characters. Okay, now let me try to explain this with few more examples, right? So if you see now these words, right, for example, organization gets one token, optimization, it gets one token, but then there are few words like standardization, globalization, right? They get split into two tokens, right? For example, global is one token, ization, and there are many words that ends with ization, and that's where you can see that all these words, we're able to use the same token of ization, and that is the concept of sub-word tokenizer, where the words are broken down to optimize the number of tokens. And if you want to see those token IDs, you can just switch to this token IDs tab, right? Okay, so that's the main concept that you need to understand about tokenization, right? And sub-word tokenizer is what all the modern LLMs use to optimize the number of tokens. So that's the key takeaway from this video. Hope you enjoyed this video. See you in the next one. Hey everyone, welcome back. Today is the day 4 of our vector database 0 to Hero series. In this video, we will understand what embedding models are and why they are so important. We'll also explore the power of vector math in embeddings with some visualizations. And then we will also explore the different types of embedding models that we have out there. And then finally, we will look at some popular embedding models used in production systems today, right? So by the end of this lecture, you will have a solid understanding about embedding. So without wasting any time, let's dive in. In the last lecture, we talked about tokens, and we understood some important concept about tokens. So tokens are nothing but converting this raw text into this numerical representation. And why we convert raw text into numerical representation is because your embedding models, they don't understand text, they only understand numbers. But the key thing that you have to keep in mind is that these numbers are just numerical representation of the raw data. These numbers, they don't carry any semantic meaning. These are just some symbols. This is not the meaning of the raw text. But then when it comes to vector databases are all about semantic search. So here at this point, a very important question comes up. If tokens are just some numerical representation of the raw data and it doesn't carry meaning, where does the meaning then come from? So that's exactly the problem that the embedding model solve. So let's try to now understand how the embedding models solve that problem. So what happens is, first, the raw data is tokenized and converted into some numerical representation, and then these tokens are given as an input to this embedding model. And then the embedding model takes these tokens and converts into vector embeddings. And these vector embeddings is what capture the semantic meaning. And as you understand, these are just nothing but some vectors in the vector space. And let's say this vector space is about 1000 dimensions. So this embedding model would then generate vector embeddings of 1000 dimensions. So you would have around 1000 numbers in this array, and these numbers are nothing but it just denotes some coordinates in the vector space. So that's what is the vector embedding. It's just some coordinates in the vector space based on the dimensions. So the core idea here is very simple. So the items or the text that has similar meaning would be closer together in the vector space, whereas the items that has different meaning would be further apart in the vector space. And since these embeddings are nothing but vectors, we can actually perform some vector calculation on these embeddings. So now to demonstrate that, let me show you some interesting examples with some visualizations. Okay, so now I am in this vector playground and the model that I'm using is the Globe 300D. Now, since these embeddings are just mathematical vectors, we can actually do math based on these vectors. For example, let's say if I were to perform this vector calculation, king minus men plus women, and try to calculate, you can see that it leads to queen. So though we never train this model, the relationships between these words are calculated based on the vector calculation. And this is very powerful. Let's take another example here. Let's say we do Delhi minus India plus Japan. And if you try to calculate that, it leads to Tokyo. So Delhi is the capital of India and Tokyo is the capital of Japan. Now, these calculations based on the vectors is very interesting because all we had to do was convert these words into vector embeddings in this vector space, and then we can perform this vector calculation. And this is exactly the concept behind semantic search, because what happens is that all the words, when they are converted into vector embeddings in the vector space, the words with similar meaning would be closer together in the vector space, whereas the words with different meaning would be further apart. And that is the basis on which we can perform vector calculation. And this is the fundamental concept that powers your vector databases. So you can perform similarity search based on these vector calculations. Okay, so just to summarize, the embeddings are nothing but just the coordinates in the vector space. Here we are plotting these words in the three-dimensional vector space, but then when we work with the real embedding models, those vector spaces tend to be higher dimensions, and all the latest embedding models, they even generate vector embeddings with almost 3000 dimensions. And that is why vector databases are heavily used in building the semantic search in the modern applications. Okay, so now let's look at the types of embedding models that we have out there. So the first type we have is, it all started with the word embeddings. So the first type is word embedding models. So what this word embedding model do is, it takes a piece of word as the input to the word embedding model. So it takes the word as the input, and the output is nothing but some embeddings, some floating point numbers. Okay, so this is what the word embeddings would do. Now, some popular examples of the word embedding models are, you have the word2vec, and then another example I can think of is globe. So these are the two popular word embedding models that we have. But the problem with word embeddings is, let's say you are trying to do embedding for the word river, and then there's another word, let's say bank, and there's another word, let's say account. Okay, so what happens in word embeddings is that the embeddings are generated for individual words. So the thing is that the main limitation is that, let's say you have a sentence river, let's say you have a sentence river bank, and you have another sentence bank account. Now, since these embeddings are generated for individual words, the thing is, we would not know what bank actually refers to in the sentence. So the main drawback of word embedding is that the context is missing in word embeddings. So that's the main limitation of word embedding models, but that is how we started. We kind of developed this word to vec and globe embedding models, which are powerful if you want to do, individual word search, but then it's not powerful when you try to find the context of that word in a given sentence. And that's the main limitation of the word embedding model. So that's the first embedding model that we have. Now, the second type of embedding model that we have is the text embedding models. This is the second type of embedding model that we have. Now, in this, as you might have guessed, here, this text embedding models, what it does is that it takes sentences, or you can even take paragraph, or the entire document can be sent to this embedding models as an input. And what it does is that it converts this sentences, paragraph, entire document into vector embeddings. So what happens is that this type of embedding models, the main advantage is that since we can embed the entire sentence, the entire paragraph, or the entire document, so based on that, you would have the embeddings generated, which means you can compare two sentences with each other. You can compare two paragraphs. You can even compare the entire document with, a search query. So that's the main power of this text embeddings. And nowadays there are many text embedding models. You have it from OpenAI, you have it from Gemini, and almost every providers out there, they have some sort of text embedding models, because that's kind of the foundation on top of which the LLMs are built. So yeah, so this is what is the text embedding models. And this is heavily used in semantic search. It is heavily used in building RAG systems and recommendation engines. So that's the text embedding model. And the third type that we have, and this is very popular nowadays, is the multimodal embeddings. Yeah, so this is the third type of embedding model, multimodal embedding. Now, what this multimodal embeddings do is that here, along with this sentence, paragraph, and entire document, you can also, generate embeddings for images. So you can also send images. So basically, this multimodal embedding, they support text plus images, and that gets converted into vector embeddings. So these are the three popular embedding model types that you would come across. Now, nobody uses word embeddings because this was just the inception of embedding models, but this kind of led into several more researches, and then the outcome was we came up with text embedding models, multimodal embedding models. But then nowadays, mostly you would be using text embedding models and multimodal embedding models in your vector database pipeline to kind of build semantic search. So if you are, let's say, building something that's purely based on text, there's no point in using multimodal embeddings. You can just build that use case using text embeddings. Whereas, let's say you kind of want to support a RAG pipeline or a document search, you want to build that on some sort of, let's say, PDF, and the PDF contains both text and images, and obviously you would go for multimodal embeddings. So that's the main power of multimodal embeddings. So these are basically the three types of embedding models that you would come across. Okay, so now here are a few popular embedding models that you should be aware of if you're building semantic search and RAG pipelines using vector databases. You have this text embedding models from OpenAI. you have from Google Gemini embedding 1. Then you have other embedding models from Cohere, and you have it from Microsoft Codebird, which is optimized for understanding code. And then recently Google released this Gemini embedding 2, which is a multimodal embedding models. And here you can see all the list of dimensions that they support. And here are the use cases. Mostly you can see the use cases are for building RAG and semantic search. Codebird is used for finding code similarity and code search, whereas this is Gemini embedding 2, which is a multimodal embedding models, and that supports both image and text search. Now don't assume these are the only embedding models out there. There are many more, but I just wanted to highlight here few popular embedding models out there at the moment. So the key takeaway from this video is that tokenization just converts raw text into numerical representation, which is then sent to the embedding model, which generates the vector embeddings so that you can perform some similarity search and build RAG pipelines and recommendation systems. So that's all in this video. Hope this video was useful, and see you in the next one. Thanks for watching. Hey everyone, welcome back. Today is the day 5 of the Vector Databases 0 to Hero series, and finally it's time for some live demo. In this video, we will explore some embedding models from Google Gemini, and then we will see some live demo where we will be generating some vector embeddings with Gemini embedding model. So without wasting any time, let's dive in. Okay, so now let's explore some embedding models from Gemini. So I am on the Gemini's API documentation page. Now here, if you just go on to this model versions, which are currently available from Gemini, the embedding models. First, we have the Gemini embeddings. The code name for the Gemini embedding model is Gemini embedding 001. What it supports as the input is text, and the output we get is the text embeddings. The input token limit is 2048, and the output dimensions are flexible. It supports anywhere between 128 to 3072 dimensions, so you can enter in any value in this range, but the recommended dimensions are 768, 1536 and 3072. And the last update for this model was in June 2025. So this is the text embedding model from Gemini. Now there is one more embedding model, that is Gemini embedding model 2. This was released in April 2026. Very recently this was released. Now the code name is Gemini embedding 2, and the interesting thing is it supports, as you can see, it supports text, image, video, audio, and even PDF as the input, and the output we get is again embeddings, right? Text embeddings. Now the input limit size is much higher here. Obviously it supports PDF, so you can imagine the input token limit is much higher, around 8192 tokens, and the output dimensions is again flexible, which you can configure, but it supports in the range of 128 to 3072. These are the recommended dimensions that you can generate. So that's the high-level overview of these two embedding models from Gemini. In our demo, we would be using this Gemini embedding model, and in the future lectures, we will also explore this Gemini embedding 2 and maybe demonstrate some multimodal embeddings as well. But in this lecture, mainly we'll focus on the Gemini embedding model. Okay, now let's jump on to Google Colab. So this notebook demonstrates creating vector embeddings with Gemini embedding model 1. So first step is we need to import all the required packages. So we need GenAI from Google. Then we also need pandas, and we need to import cosine similarity from sklearn. These are the few important packages that you need to import. The next, what we are trying to do is we are trying to get the API key from Google Colab. So I have configured this API key here. So you can see under secrets, I have this configured Google API key. So make sure you have generated the Google API key for accessing the embedding model. Now, once the API key is available, using that API key, you can generate a GenAI client. So this is how you do that. And then here in the next step, what I have is a list of text. I have an array of sentences here. And what I'm trying to do here is that I'm just trying to give that this list of text as an input to the embedding model. So what I'm doing here is client.models.embed content. You remember in the previous step, we created this GenAI client. So using that client, you can start embedding your documents. What you need to pass in here is the model name that you want to use and the contents and some optional configuration. This is what you can basically define here. Here's an example in the documentation. So as you can see here, I have given the model name as Gemini embedding 001. This is the content is nothing but that area of text that I have, and then some configuration. What I'm telling here in the config file is that the output dimensionality I want is 768 and the task type is semantic similarity. So that's how you can generate those embeddings. And then once we get the result from this API, what we have here is we're just basically looping through that result and just printing those embeddings. So let's try to now run this. Okay, so first let's try to run this import required packages. Then let's run this set API key. And then this is the interesting step here. We'll try to now generate the embeddings. So let's try to run that. So if you see here now, what we have is that for all those examples, we are able to generate the embedding. So you can say, how do I write a Python function? For that, the embedding length was 768. 768 is what we have defined. So all the output would be of this dimension, 768. And you can see for each text, you have this embeddings. So if you see this array is of length 768 because there are 768, embeddings that are getting generated because this is 768 vector space. So all these examples are of dimensions 768. Okay. Now from these embeddings, it's not clear which sentences are similar to each other and which are not. For that, what I've done here is that we're using pandas and using cosine similarity. Let's try to generate a similarity matrix. So if you now look at the similarity matrix, you'll find something very interesting. For example, if you see this example, how do I write a Python function? This has the highest similarity with how can I write a class in Java. Then if you see some other example, like which smartphone has the best camera, obviously you can see that the highest similarity is with what is the best Android phone. So this too has the highest similarity. Now let's take another example. Let's say turn off the lights. This has the highest similarity with switch off the lights. Wow, this really is interesting stuff. Like using the vector embeddings, we are able to find from this list which sentences are similar. And then you can understand the power of this vector embeddings because we can then find similarity search. Now let's take this similarity matrix to another level. Let's try to visualize this. So if we need to visualize in a 3D space, we can do that using PCA. What is PCA? PCA stands for Principal Component Analysis. So what it does is that PCA, in short, it reduces the number of dimensions in the data while keeping as much as important information as possible. So you can imagine that these vector embeddings are of 768 dimensions. Now as humans, we can't visualize something in 768 dimensions. And that is where the concept of PCA comes into the picture. So it reduces 768 dimensions to 3 dimensions so that we can visualize this in 3-dimensional space. So now here is the code how we can generate that visualization. Now I'll not go through this code here in detail because that's not the scope of this video. But if I just try to run this, you can see that we can now visualize this sentence embeddings in 3-dimensional space. Okay. Now this is obviously static. There's another way you can do it to make it a little more dynamic. You can do it using Plotly. So if I just run that, okay, and this is much more interactive. So you can see here now that, for example, these two sentences, how can I create class in Java and how do I write a Python function? You can see that those are closely related. Then you can see the next example here. What is the best Android phone and which smartphone has the best camera? Those are, again, similar, and that's why the distance between them is very less. So this is how you can visualize these embeddings and see which sentences are similar and which are not. So this is really a very powerful concept, and I would urge you to kind of play with this notebook. You can come here and change the sentences. That's all you need to do, and you can just play with it and see what output you get. So that's all I wanted to cover in this video, that how we can generate embeddings using the Gemini embedding model. Hope you found this video useful. See you in the next one. Thanks for watching. Hey everyone, welcome back. Today is the day 6 of our Vector Databases 0 to Hero series. In this video, we will explore the key components of a vector database, and we'll also see how these components work together to make the similarity search extremely fast and scalable. So by the end of this lecture, you will have a solid understanding of how a vector database store, index, and retrieve high-dimensional vector embeddings efficiently. So without wasting any time, let's dive in. Now let's learn the high-level design of a vector database. So earlier, we learned the high-level pipeline of a vector database. Now let's try to understand how the internal architecture of a vector database looks like. Like, we'll understand how a vector database actually stores vectors and how they index those vectors and how those vectors are fetched from the vector database. So here are the key components that you would come across in a vector database. So first, we have the API gateway, and then we have the indexing layer, and there's a query processing layer, and then we also have a storage layer. So these are the internal components that you will come across in every vector database out there. So the entry point to a vector database is always the API gateway. So the responsibilities of an API gateway is that this is what interacts with the vector database. And the responsibility of this API gateway is to expose those APIs so that the client application can store vectors, they can basically update vectors, they can read those vectors or delete those vectors. For performing all these operations, the API gateway exposes those APIs so that the client application can perform those operations. So that's the main responsibility of the API gateway. And it also exposes some APIs for querying those vectors. And one thing to note here is that these operations are different from querying vectors, because this is where you kind of perform these operations in the ingestion phase when you are actually storing those documents inside a vector database, whereas the query operation happens when you wanted to search something. So these are two different operations that any client application would perform in any vector database, and that's the responsibility of the API gateway, is to expose those APIs to the client application. So that's the responsibility of the API gateway. Then we have the indexing layer. The purpose of this indexing layer is to organize those vectors for efficient similarity search. And this is nothing new. You would come across indexing layer in any database, be it any traditional database like SQL, NoSQL. You have that indexing layer. Similar to that, even in vector database, you would come across an indexing layer. The main purpose of indexing layer is efficient similarity search and avoid the brute force search. So now for indexing, there are two techniques that most of the vector databases apply. One is IVF. Now IVF stands for inverted file index. Okay, this is one technique that most of the vector databases use for indexing. And there is one more popular indexing technique, that is HNSW, which stands for hierarchical navigable small words. So these are the two key techniques that most of the vector databases apply in the indexing layer. And as I said, the main responsibility for the indexing layer is to enable fast search, right? Low latency search, so that you can search millions of vectors inside this storage layer efficiently. That's the purpose of this indexing layer. Next, we have the storage layer. Now, storage layer is obviously for storing those high dimensional vectors efficiently. And the main feature of any storage layer is obviously fast insertion, fast retrieval, and fast deletion. Those operations should be extremely fast. And then the storage layer also ensures that there is high durability and high reliability. Now, how it enforces high durability and reliability is by replication. So this layer can be replicated for any fault tolerance, and there could be even partitioning done if you want to scale. So you need to do partitioning. These are all the fundamental techniques that you would find in any database, and those techniques are also available inside any vector database that you would want to use for production grade solutions. So that's the responsibility of this storage layer. And then there is another layer that is for the query processing layer. Now this layer handles any query vectors. So whenever any client application, they search any query vector, it's always the responsibility of this query processing layer that ensures that this incoming query is handled efficiently. So the responsibility of this query processing layer is to handle those incoming search queries, and then this layer coordinates with the indexing layer and the storage layer. And this is where it uses those techniques of filtering and ranking those results once those results are fetched. So that's the responsibility of the query processing layer. So just to recap here, these are the key components that you would find in any vector database. So you have the API gateway, which is like the entry point. Then you have the indexing layer that ensures that whatever you search is always fast and efficient. Then you have the storage layer, which is for your data persistence. And then you have the query processing layer that always ensures that the query vectors are matched against whatever is stored inside this storage layer. So these are the 4 key components that you would find in any vector database. Hope you found this video useful. See you in the next one. Thanks for watching. Hey everyone, welcome back. Finally, it's the moment we all have been waiting for. In this demo, we will be generating embeddings and storing those embeddings in ChromaDB. And then we will perform some semantic search queries using ChromaDB. So without wasting any time, let's dive in. Okay, so it's time for a live demo. In this demo, we will be storing and querying vector embeddings using ChromaDB. So the first step here is to import the required packages. We need the Gemini package from Google for creating the Gemini client. And all we need here is we need to pass the API key, which I have it in my secrets here. Under secrets, you would find that I have this API key which is stored. So you would need to generate that API key before creating any GenAI client from Gemini. So let's try to import these packages, and then let's set the API key. And then the third step is we need to now generate the vector embeddings using the Gemini embedding model. And this is exactly the same example that we saw in the previous lecture, where we generated the vector embeddings using the Gemini embedding model. So here what I have is I have a list of text that I am passing inside this content, because I want to generate the vector embeddings for all this text. And for that, you need to just invoke client.models.embed content. What the embed content supports is the arguments it supports is you need to pass in the model that you want to use for generating those vector embeddings. You need to pass in the content, and you can also pass in some additional configuration. So here in this configuration, we are passing the output dimensionality, which is 768. You can pass up to 3072 dimensions, but the optimal dimensions are 768, 1536, or 3072. These are the optimal dimensions that you can use. Here for this example, I'm using here 768 as the dimension. So this is where it would invoke that embedding model and generate the vector embeddings. And here we're just iterating through those generated vector embeddings and printing it out here. So if we just try to run this steps, so this is executed now. If you see here, we now have vector embeddings which are generated for all those texts that we have in this list. So that's the first step. We are now done with generating vector embeddings using the Gemini embedding model. Now, the next step is we want to now store these vector embeddings inside ChromaDB. So for that, you will have to install the ChromaDB. So for that, you can use pip install ChromaDB. If you just click on that, it will try to install all those packages in your machine. So yeah, it's done. If you're doing it for the first time, it might take a little bit longer for you. So that's done. So now in the next step, we can store those vector embeddings inside ChromaDB. So for that, the first thing is that we'll have to create a ChromaDB client. For that, you can just say ChromaDB.client, and these are the imports. Make sure you have these imports after installing the ChromaDB package. So using this ChromaDB.client, you can get the ChromaDB client, and this is where I am setting the persist directory where I want to, have the data persisted on my machine. So this is how you create the ChromaDB client. Next step is you need to create a collection. What is a collection? Collection is just like a table in a database. So similar to how we have table in SQL database, and you also have collections in NoSQL database. Similar to that, you can create, a collection. So for that, you can use this method get or create collection. So if this collection does not exist, it will create a new one. So here I am defining a collection name, CodedX ChromaDB demo. This is where I want to store those vector embeddings. So this is the collection. Now, once the collection is created, before you add this onto the collection, whatever vector embeddings we generated. So if you can recall, we generated the vector embeddings inside this result variable. So if you see here, we have all those vector embeddings inside result. So here, all we are doing is that we are extracting those embeddings and storing it in this embeddings array. So that's how we can extract those embeddings, and we have inside the documents, we are assigning all those texts. Is this text defined? Text is where we have defined all the list of text. So what we are doing here is, along with the vector embeddings for each text, we are also storing the actual text. So you have your documents, and then you also have the embeddings for those documents. And then We are also assigning some IDs for those records inside this collection. So if you just run this now, yeah, so you can see that embeddings are stored successfully. So we are now done with storing embeddings in ChromaDB. So now is the interesting part. How do we now query these vector embeddings inside the ChromaDB? So here I have a query. This is a query. So what I would do here is that you can use now for querying, you can use client.models embed. So this is the, the important step here. This is something we covered in our vector database pipeline as well, that before you query anything, you will have to generate the query embedding. So you will have to generate the query embedding using the same model and dimension. If you don't use the same model, for example, for all our initial text for storing those vectors, we use the Gemini embedding 001. Now, you cannot use any other embedding model. It has to be the same embedding model. And also, it has to be the same dimension. If you just use some other dimension here in your query embedding, it would not work, because the query embedding and the embeddings which are stored inside the vector database has to match. So that is why this step is so important. So how we generate the query embedding is, again, we use the same client. Now this is the client from the GenAI, Google GenAI, and using that client .models.embed content, where you need to pass in the model name, you need to pass in the content. Here the content is your query, and you can also pass in the configuration. The default dimension is 3072. So make sure you always define this dimension. So once you have that, you would get the query embedding, and then that query embedding can be now used for querying your ChromaDB collection. So this is your ChromaDB collection, where you can say collection.query, and you need to pass in the query embedding. And here we are basically expecting how many results, what would be the number of results that it should return from this collection based on the query. So if we now try to run this, here my query is programming. So if I just try to run this, you would see something very interesting. We are getting these two text as the output. How do I write a Python function, and how can I create a class in Java? These are the texts that we initially stored inside the vector database. So if you see now, out of this text, when you search programming, these are the two texts that matches that. Now, what is interesting here is that in these two texts, you don't have programming anywhere. That keyword is not present inside these two texts, but still it is able to match those texts which relate to programming. And that's the power of semantic search. This is something you cannot achieve using the normal keyword-based search, because if you perform a keyword-based search with programming, you would not get this two text. Now, let's take another example. Let's say I search in here, let's say electronics. Now, if you just search electronics here, so this is what we get. Apple released a new iPhone. Which smartphone has the best camera? Now, this two text relates to electronics, and that's the power of semantic search. So that is why vector databases are so powerful. This is what powers your recommendation system. That is why all the popular, e-commerce websites that you have out there, they nowadays use vector databases and vector search for performing semantic search and recommendation engine. Also, hope this video was interesting. Thanks for watching, and see you in the next one.